My name is BETOFE MBOYO KEYTA. I'm going to speak about the maximum likelihood estimation. As contents, I'm going to give the brief introduction about parameter estimation and then the explanation of the maximum likelihood estimation. As parameter estimation, it can be defined as a process of using sample data to estimate the parameters of the selected distribution. Means the action of sharing something out among a number of recipients. There are many procedures. We have maximum likelihood estimation, we have Bayesian estimation, and more others. Those are procedures that can be used for the estimation. Maximum likelihood estimation view parameters as quantities whose values are fixed but unknown. As an example, if a population is known to follow a normal distribution, but the mean and the variance are not known, the maximum likelihood can be used to estimate them using a limited sample of the population by finding a particular values of the mean and the variance so that the observation is the most likely result to have occurred. Means what you're going to be estimating has to be close to the expected value. And compared to the Bayesian estimation, there it views parameters as random variables having some known priori distribution. And priori distribution is what? Is just the use of the logic to estimate an event. Example, a company can make profits, suffer a loss, or break in a given year. We can conclude that there is a 1/3 a priori probability of each scenario to occur. Now, let's take this simple illustration. Maximum likelihood estimation. Simple illustration. This is the likelihood of observing the data. And what we want is, we want the location that maximizes the likelihood of observing the weights we measure. Okay, now we see using normal distribution which location the mean maximizes the likelihood of observing weights we measure. And we know that for normal distribution, we expect the most of the measurement to be close to the mean or the average. As we see, most of the measurements are what? Are close to the mean. Secondly is what? The measurements are expected to be relatively symmetrical around the mean. It is also the case of what we are having in our illustration. Okay, and this one is the location that we are seeking for. And this will be what? The location that maximizes the likelihood. Now next, let D contain n samples like from x1 to xn, and they are drawn independently. How to express the likelihood function? This is the way of expressing the likelihood function. And the maximum likelihood estimate of theta means of the parameter will be the value that maximizes what? The probability of obtaining that parameter. Okay, represented as what? As theta cap means estimated of theta. And to make work easier, we can use the log likelihood function. And this one is the way of expressing what the likelihood function in terms of log likelihood. Why we have decided to use the log likelihoods? Because the log function help us to do what? To represent large values or large numbers easily and makes work easy. Okay, this one is the log representation, and this one is what? Is just the product of the gradients and the log. Why it is used? A set of necessary conditions for the maximum likelihood estimate for theta can be obtained from the set of P equations. Of the equation of these equations means the products of the gradients and the log likelihood function will give us what? The necessary conditions for the maximum likelihood estimate for theta. Now, maximum likelihood estimation, we're going to speak about two different cases. The first case is where the mean is not known, and the other one is where the mean and the covariance are both not known. Samples are drawn from multivariate normal population with mean and covariance matrix that we know. Xk is just the sample point. Theta is a function of the mean, means the parameter to be estimated, and the logarithm of the likelihood we just expressed as written, and taking the gradient of the likelihood, I want to obtain what? This final result. Means while solving, I want to come across this kind of result. The maximum likelihood must satisfy what? This condition means the product of the gradient and the log likelihood function has to be equals to 0. And that's what we said before. This is the condition that has to be satisfied. And after all operation, we are obtaining what? We are obtaining that the maximum likelihoods is just the arithmetic average of the training samples. As we can see, the estimate of the mean is just equals to what? 1 over n. N is what? Number of samples, and the sum of all of them from 1 to n. Second case is where the mean and the covariance are both unknown. Means we have in this case two parameters to be estimated. Samples are drawn from multivariate normal population with mean and covariance matrix. Xk is the sample point. Theta is the function of the mean and the covariance. And different from the previous case, here we have now parameters. Theta 1 is equals to the mean, and theta 2 is what? The covariance. The logarithm of the likelihoods will be expressed as written over here. Means after the operation we came across this result. And now taking the gradient of the likelihoods, I want to find what? I want to find this result. This one is what? Is just the gradient of the likelihood. taking the gradient of the likelihood, I want to come across this result by replacing the estimate of the mean by the estimate of theta 1 and estimate of the covariance by the estimate of theta 2. I find that expressions are what? The estimate of the mean will be equals to 1 over n, the sum from 1 to n xk, means it can be defined as the average of all the estimated mean. And the same case for the covariance also, it can be defined as the average of all the estimated covariance. As conclusion, the maximum likelihood estimate for the covariance is biased. Biased means the expected values minus the actual values do not give us 0. Means they are not equal. And then the maximum likelihood estimator is consistent. That means its bias converges to 0 as n increases. When n goes to infinity, the bias converges to 0. Means we are going to obtain a more accurate value when the number of samples increases. The best estimate is the one that maximizes the probability of obtaining the samples actually observed. Thank you.